So we are going to be going over rational functions. A rational function is a function that can be written as a quotient of two polynomials. So that means that the numerator is going to be a polynomial and the denominator will be a polynomial. So we have f of x is equal to 2x to the third plus 4x to the second, and that's divided by 4x to the fourth minus 3x. We can see that these two expressions can be simplified. They both have an x, so let me factor out an x. So we take out an x. We have 2x to the second plus 4x, and then we're going to do the same thing in the denominator, so x 4x to the third minus 3. These two x's cancel, so the polynomial that we want to deal with is 2x to the second plus 4x over 4x to the third minus 3. So we are going to put emphasis on a polynomial that is completely simplified. That is a rational function that we're going to be paying attention to. An asymptote is going to be a line or a curve that approaches a given curve, and they get very, very close to each other, but they don't cross each other. So if we have a graph, and let's say that this red line is your rational function, in this case, you're going to have two asymptotes. You're going to have a horizontal right here, that this blue line is not being crossed by the red lines, and then you are also going to have a vertical one right here. So our graphs will get really, really close to it, but they will never touch it. When it comes to vertical asymptotes, we're going to say that f is going to be a rational function, and anytime that we have a rational function, we write it like this. So this means that this is going to be a polynomial divided by another polynomial. And something very important that we have right here is that they have no common factors. So we have two polynomials, one dividing the other, and we know that there are no common factors between the two polynomials. We say that f of x, so a rational function, has vertical asymptotes in all the zeros of the denominator. So you're going to look for all the zeros in your denominator. So whatever polynomial you have there, you make it equal to 0. You may be able to use the quadratic formula. You can do factoring. If you have something to the third power, you may use the prime factorization theorem. But if you have something higher than that, that's when you're going to have to use the fundamental theorem of algebra, and you have to do P over Q. To find the horizontal asymptote, what we're going to be paying attention to is going to be the exponents. So we are going to have three different cases. The first one, in this case, is we're going to be comparing the degree of n and m. So if the exponent of the numerator n is smaller than the one in the denominator, then automatically we know that y equals 0 is going to be your horizontal asymptote. The second case is when n is equal to m. So if the degree from the numerator and the degree from the denominator are the same, then what you're going to do is get the leading coefficient of the numerator and divide that by the leading coefficient of the denominator. And I'll give you an example right here. If we had f of x is equal to 4x to the third plus 2x minus 1, and your denominator was 2x to the third minus 8. The only thing that we're going to do is get the leading coefficient from the numerator, which is 4, and divide it by the denominator, which is 2. So that means that our line needs to be at y is equal to 2. The third case is if n is greater than m, then the graph of f has no horizontal asymptotes. So in this case, you're going to have to find the horizontal and vertical asymptotes of the graph of a rational function. So we're going to start by finding the horizontal asymptote. And we have three cases. We have it's either n is less than m, n is equal to m, or n is greater than m. In this problem, we see that n is 1 and m is 2. So the exponent in the denominator is greater than the one in the numerator. So we are going to get our first case, and our first case is y is equal to 0. So in this case, our horizontal asymptote is y is equal to 0. Now, to find the vertical asymptote, we need to make the denominator equal to 0. And we just need to do this algebraically in this case. So we are going to add 1 to both sides. Divide by 4. Divide by 4. And we have x squared is equal to 1 over 4. You'll find the square root. So x is going to be plus or minus 1 over 2. So our horizontal asymptote is going to be at x is equal to negative 1/2 and also at 1/2. So again, we're going to begin with the horizontal asymptote, in this case, we have the exponents being the same. So to find that, we're going to get the leading coefficient, which is 2 divided by 1. So our asymptote is going to be our y equals 2. And to find the vertical asymptote, you make x to the second minus 1 equals 0. So add 1 to both sides. X squared is equal to 1. Find the square root. So square root, you get x is equal to plus or minus 1. If we graph f of x equals x to the second minus 25 over x to the second plus 5x, this is not in the simplest form. We can actually simplify this a little bit more, and we can get x minus 5, x plus 5. And that's your numerator. And in the denominator, you get x plus 5. So we can actually cancel the x plus 5, x plus 5. So that doesn't become a vertical asymptote. That's why in our graph, we don't have a line right here. And we actually only have the asymptote right here. But some graphing tools like Desmos, sometimes they don't show you the holes. But if you were looking for two asymptotes and you see it that there's not one in the graph, that means that you need to have a hole in that point. Using a different tool, we're going to see how it was supposed to look. So in this case, one is free with GeoGebra, the green one is with GeoGebra, and you can see that there's a little tiny hole right there. So that means that our graph doesn't go through that point, but it gets really close to that point. So instead of creating an asymptote, now we're creating a hole. And that is the next part of the lesson. Whenever you have polynomials or factors of the polynomial in the numerator and the denominator, they cancel each other out, is going to create a hole. It's not going to be a vertical asymptote based on one of the zeros because you're able to cancel with the factor of the denominator from the numerator, you're going to get a hole. And you can see that in the previous example. So in this case, we're going to be paying attention on three different things. We have horizontal, vertical, and we are also going to be looking for holes. The way that this is written is slightly different because this is not simplified. So it may get a little confusing when you're finding the horizontal asymptote. So we're going to rewrite this so you can see it first for the horizontal. So you have 2x plus x to the second divided by x minus x to the second. The leading coefficient is not going to be the one in the front, but it's going to be with the one with the highest degree. So we're going to divide. So for the horizontal asymptote, you're going to divide the coefficient of the numerator, which is 1, and the denominator, which is -1. And that means that our answer is going to be -1. So that's going to be our horizontal asymptote. To find the vertical asymptote, we just need to make the denominator equal to 0. Okay. So we're going to get negative x to the second plus x is equal to 0. We're going to factor out on x. We get negative x plus 1 is equal to 0. So we have x is equal to 0. That's our first one. And then we have negative x plus 1 is equal to 0. So minus 1, negative x is equal to negative 1. So x is equal to 1. Okay. So your vertical asymptote is at x equal to 0 and x is equal to 1. And to find the whole, we're going to simplify the expression. So on the top we can factor out an x. So we have x, 2 plus x, and then we have x, 1 minus x. You can see that the x's right here cancel. So that means that we're going to have a whole at x is equal to 0. And because we already have a whole at x equal to 0, we're actually going to cancel it from the vertical asymptote. So it's not going to be an asymptote anymore, it's going to be a whole. So the oblique asymptote will only be in a rational function whenever the numerator is exactly 1 degree higher. So the numerator needs to be 1 degree higher than the denominator. So if this is 3, this one will have to be 2. That's the only way that you can find an oblique asymptote. And to find it, we are going to divide the numerator by the denominator using long division. When you do long division, you're going to get a linear equation, and that's going to be your oblique asymptote. We don't care about the remainder. So for this problem, you have to find the horizontal, vertical, oblique, and or holes. So we're going to start with the horizontal. Based on the definition that we had, because this numerator is greater than the denominator, we have no horizontal asymptote. So we're going to put no asymptote, right? Then we're going to find the vertical. To find the vertical, we just need to get the denominator and make it equal to 0. So we're going to do 2x minus 4 is equal to 0. So plus 4, 2x is equal to 4, divide by 2, divide by 2. So we have x is equal to 2. So that's going to be our vertical asymptote. We cannot factor this one. That's going to be the simplest form. If we were to factor the numerator, we will get x plus 3 and x minus 3. But that's not going to cancel anything right here. So we know that we're not going to have a whole. So we don't need this part. Now, in this case, we know that the degree from the numerator is 2 and the degree from the denominator is 1. So we are going to use long division. So when we do long division, we have x to the second minus 9, and we're going to divide by 2x minus 4. We need to make this 2 into a 1, so that's going to be 1/2 x, and that's going to give us negative x to the second, and that's going to give us positive 2x. This cancels, and we have 2x minus 9, and we're going to multiply by 1, negative 2x plus 4, cancel, and our remainder is going to be negative 5. So the equation of the oblique asymptote is going to be y is equal to 1/2 x plus 1.